Hey everybody, this is Larry. This is February 11th, and I am doing an extra problem for practice, a premium question. So that's one that I haven't done yet, and then that's RNG one, and hopefully it's not a SQL question. Let's try again. I think I have to reset this because last time it didn't give me a premium question, even though the to-do one was fine. So maybe there's a bug there. Okay. So yeah, let's take a look at this. Today's problem is 2123. Minimum operations to remove adjacent ones in matrix. Hit the like button, hit the subscribe button, join me on Discord. Let me know if you like these premium problem videos, because I honestly don't get that much traffic on it relatively, and so I don't know. Maybe one day I'll stop doing them if people don't care about it. But if people do care about it, let me know. Or if you have a request and I haven't have a video on it or something like this, let me know in the comments as well. Because for me, they're all effectively random. I haven't seen them before, so yeah. So anyway, you're given a binary matrix grid. Okay, you can flip one in the grid to be zero, right? And a binary matrix is well isolated if there's no one in the matrix that is four directionally connected to another one. Return the minimum number of operations to make grid well isolated. Okay. That is an interesting problem. The first thing I notice is that n and m is going to be 300. So, I don't know. Is it going to be linear? I guess so, right? Or at first, I don't know. Linear seems okay. My first kind of thing is that it's very hard, isn't it? I mean, my first inclination is thinking about like a chessboard, right, where you have colors, white colors and yellow colors, and then basically for to minimize the number of things you have to disconnect, then you either take the black colors and then the white colors, right, and then for each island you might have to choose the minimum of those two. I believe that should be right. And what I mean by that is that, for example, if you have something like, only horizontal. Okay, so you have something like this, and I don't know, maybe you could whatever. You have to treat the ones in the upper left differently from the ones in the upper bottom right, because if you try to put the same checkerboard on it, it may be wrong, right? And I think the checkerboard or chessboard analogy kind of also reminds me, or at least allows me to make the second observation about how this is actually, in this way, a bipartite graph. And having a bipartite graph means that now you can, and some of this is just from experience, meaning that, to disconnect a bipartite graph, you just take the minimum of, like if you visualize putting a bipartite graph, once on the left side and once on the right side, you take the minimum of either of those two, and you do it for each island. I think that should give us the answer. And yeah, it should be good enough for me to get started. So, I mean, and if it's wrong, then I said a lot of stuff for no reason anyway, right? So, and then we can see where I went wrong, right? So yeah, so done. Right. So if this is not done, then we go calculate it, right? We calculate xy, say. Calculate such a, but yeah, it's fine. AB, right? Maybe just, and then total is equal to 0, and then we return total, and then maybe this returns a thing anyway, so then we could just do a min of this, and then total we add it, right? And what I mean by that is that calculate, I need to add a color, I think, make this slightly better, but yeah, and the color just is based off the idea that it's bipartite, right? Meaning that it was bipartite. Oh, and I kind of missed a thing here, is if grid of xy is equal to 1. And then we also want to add a direction thing for the 4 directional. But yeah, the color thing is just strictly, at least for me, based off the bipartite thing, because then now you have the left side or the right side, and you could also think about the colorable, and of course, bipartite graphs are two colorable, right? That's just also another way to say it and another definition. Okay, right, so yeah, and all these things will be bipartite anyway, so we don't have to check for odd cycles or something like that, right? I think by definition it should be okay. So yeah, is equal to true. So for dx dy in directions, right? If grid of nx and y is equal to 1 and not done of nx and y, and we have to check the bounds. Right, and then yeah, and then we can calculate nx and y, and then 1 minus color. This just flips it from 0 to 1 and or 1 to 0. You can maybe also just like XOR it by 1 or something, right? So then now we return yeah, so let's just say what we return is the 2 colors. So yeah, right, so then now R for results, and then ends right, and then here actually we want color to be 1. I think that's mostly good, maybe, unless I have some infinite loop thing. Let's give it a quick submit. Hopefully I didn't miss an weird edge case, and I did miss a weird edge case, it seems like. Let's see if I could visualize this in big. Or at least I don't know if it's a weird edge case. It's just that my assumption is wrong then. Let's see. So I have it wrong for this one. Tell me why. So here I claimed that 5 would be enough because I assumed that's bipartite, but it seems like 3 is enough. 1, 2, and then 3. So I'm wrong in that the checkerboard bipartite thing is, or at least I'm wrong in that this is it is optimal. So now I have to kind of rethink everything. That's hard then. 300 thing. Let's see. So I'm very wrong on this one, by the way. So so disregard everything I said up to this video. Because basically my hypothesis in the way that it was is that it's going to be greedy, but then now and in part of that greedy is that you never remove 2 things that are next to each other, but it seems like now you would want to, or like there's a case where that is not true. So yeah, so basically we're just here, and then I assume here and just one of these 2, right? After this, how do I make that decision in a good way? Because basically what I am doing is this instead. Can I save it from this answer, right? And that is just too much. That's interesting. So there is another way to disconnect this without I do wonder if this is a case analysis problem, because I don't know that I have a good intuition about this now. This is a good warm-up problem to the contest that we have in like 2 hours, though I need to get some food. Maybe that's but how do I think about this then? I don't. All right. I think one thing that I'm trying to figure out is whether I can still use the graph visualization that I had, which is this bipartiteness. Because then, if you think about how to draw it, maybe I was gonna draw in my notebook, but oops. But maybe I'll bring up the paintbrush real quick. But basically, the idea is that now I have something like what do I have, right? So basically, you can represent the thing something like this as to, and then you have something like this, and then this, right? And what I was doing is that I was like, okay, let's just take the left or the right, but clearly that's not exactly true. What you want is actually this one, and this one, right? So this is why I got 5 and instead of 3. How do I determine which? I mean, without like, I'm trying to think of it as from as simple as possible as well, because I think maybe there's some bridge E things that we can think about, but I'm not even convinced that the bridge idea is, you know, there's a lot more proofs if that's the way to go, right? I feel like there's a lot of weird whatchamacallit, at possible edge cases. That's why I'm a little bit curious on how to handle it. For example, what if, so this is basically if the ones look like this, what if I also have this other thing here, this node that connects these two, and then now it looks like this, and then is still a DP? Don't think so. Or at least not an obvious one to me. That is because basically adding this other edge, what does that mean, right? That means that I'm connecting like these two or something like this. And I don't know that that changes things significantly. I mean, then now we would, like, this is not enough, or then we have to do these two and this one. And one of these two still. So it'll be 4, but how do we determine that in a good way? It's 300 square again. 90,000. I think another way that I'm thinking about is maybe some sort of binary search, but that's a very hard binary search to kind of prove. And the idea here is that if we binary search, can we remove something greedily? I don't know. I feel like I don't think you could really remove stuff with binary search. And I don't even know that this is the worst case, or like there is some additional complexity. Like for example, we just double this in height, right? Like if the input looks like this, then what does that mean, right? That means that we have 4 and then 4, so this is 8 as an answer. But I don't know what that represents for me. The way that I have it now, it may actually be 8 just because of actually it would just be I don't know, it would be 8. It will be let's see, actually it would be 10 the way that I calculate this, so it would still be wrong. We don't know off my head now. Thought I did. So the checkerboard or the chessboard analogy is or idea is not quite right. Let me see. So now I I think the hard part is that you cannot move. I assume that you, for some reason, I mean, I don't know. I thought that one or the optimal solution would not require deleting adjacent ones, but clearly that is the solution, or that is at least one of the solutions. So then now I have to rethink, and then that super invalidates the chessboard or checkerboard idea. I'm trying to think whether it ever makes sense. Like, can you do greedy and then like, does it ever make sense? I mean, I think I'm giving it another minute mentally. If I still don't have it, oh, right, sorry. I think I still have this thing up. Let me take it off because I'm not looking at it. This was the thing that I was talking about. I forgot to, but yeah, I mean, I think if I don't have any idea, I'm going to try a greedy and then see where it gets me, right? Is there another way to count this in a good way? Like, what if I just do something greedy like this of pre-filtering of like something like if what's it called, grid of xy is equal to 1 and all of the you know, for dx dy in directions yeah, this is annoying to and or adjacent. I just put in a thing, right? Then grid of xy is equal to 0, total increment by 1. I don't know if this is good, right? For example, but that is like, and then just run the thing afterwards, which is a little bit awkward, maybe. But all right, let's give it a try because I have no idea. So this is going to be one of those things where we're exploring things. I in a contest or whatever, especially in one where they don't give you the wrong answer, I might actually like do this and then after that kind of see how that adjusts different inputs. But for now, I might just use the wrong answers to cheat. But okay, but yeah, so for dx, dy, and directions, basically this thing, or whatever. Right, maybe that's a little bit cleaner. Where is it? Tell me why. Yeah. Let me get the one that I got wrong first as well, obviously. No point of, I mean, I know that I said out YOLO, but I mean, that's silly YOLO if you don't even at least get the one that you got right. It does fix that. Let me add the other one where it's this, but doubled it. Let's give it a submit. I don't expect this to be right, to be honest. Yeah, This is a case that I actually was thinking about when I said checkerboard, but now I don't know how to reconcile the two in a not in a way that is you know, other than adding even more random inputs or like edge cases type thing. Yeah. For example, I don't. This is just like me trying random things, like I would if I was doing a contest, because having an AC is better than no AC. But I don't think now I have strong foundational basis. But yeah, let's see. Let's just say we have some get min. Right. And then basically, right, so this works for now, right? Oh, I have to get the other case where it is odd number of things. So then now it's return the wrong one. Verify that your things are wrong before you can't do them. But and now we can remove this part for now. Don't try this at home, friends. It is kind of pretty bad. I mean, I knew that it would work for this, but I don't know that I have a proof for all cases, and clearly it doesn't. So yeah, but I'm doing it the old-fashioned, silly way of learning, maybe, and exploring the problems. And I think also, to be honest, I am just being lazy today. I think in general, the way that I'm doing it, or the way that I'm testing it, is fine, but I wouldn't. I shouldn't submit it. I should. There is some value in kind of learning. There is some value in kind of finding these edge cases yourself, especially for if you're into competitive programming, and most judges won't give you the test cases, right? So yeah, and this is an example of trying to do test cases. And the thing that I'm doing here is that I remove this one, and then now I think I removed that one, and then now I try to do I think everything is awkward, but and then now 2, 3, and then 4, 5. Okay, but the optimal is actually 4, which is, what is the 4 that we would, maybe 1, 2, 3, 4, maybe? No, that's not right, right? Which is the 4? So 1, 2, 3, 4. Huh. Huh. I really have no idea right now, to be frank. This is indeed a hard problem. Don't know why they didn't use it on a contest. This is a good. I feel like this is actually a good contest problem. I would be struggling. Okay, actually, why did I delete this? All right, let's see. Okay, so my my hacked solution doesn't seem like it will work. So, so we have to do a little bit better. As we said, what did I say was the solution again? I'm trying to see if I could figure out how to codify this. 2, 3, 4, right? And we can really, brute force in a good way. And of course, it's really hard to kind of have like an edge case analysis type thing, or kind of implement a solution that is exhaustive edge case things, because each of these are island component, right? You can merge this with the previous one, and that would just be no go. So I do want to remove this then. It's just that, even though that was my first thing, it's just that, okay, so my greedy algorithm just removed this, but then afterwards you have this big island, and it just turns out that this thing, even without the greediness, we want to do this, and then this, and then this. I wonder if can we just sort by these things and then do it that way? Would that work? Like this is a 4, and then now this is a 3, and then one of the 2s, but then you don't know which 2, right? Because if you did this 2 by accident, then you get 5 as well. So it's not good enough, right? Wow, I really have no idea how to do this. I feel like I'm missing an observation. 300 squares, so there's no, yeah, okay. Huh. Fairly struggling with this one. Yeah, I don't know that greedy. You can do some sort of greedy, but then, okay. Another way that I could think about it is just thinking about the depth first search tree, but let's say I start here. If I, the thing is that we don't know, or I don't know anyway. Maybe the viewers at home already do. I don't know how to start at a, or like, given a 1 that's in the beginning, I don't know how to know that whether this is the one that'll be at the end, right? Maybe that's another way of thinking about it. Is there a heuristic that allow us to see if a particular 1 will be at the end thing? Really have no idea, to be frank. I really thought that, I mean, there is definitely an island component, but even within an island, there's clearly much more complicated things. And in this case, the solution is all the ones that we're deleting are together. So the checkerboard thing is really messed up here, right? And it is wild, isn't it? Is there a max flow type thing? Is there a... Yeah, we don't have any idea. Wow. I feel like I need a hint. I guess there's a hint button. Alright, let me get one hint. Yeah, I got the biproduct route. You want to find the smallest set of vertices such that every edge in the graph has an endpoint set. Isn't that what I mean, I did this already, but maybe I did it wrong. Oh. I mean, maximum bipartite matching. How am I thinking about this again? The hint. I tried to not read the last couple of hints because I think it was giving away too much. Nope. Yeah. Or starting to. I mean, I did the bipartite graph, and then basically. Let me bring up my drawing again. Maybe I can think about it that way. So the hint is bipartite graphs. Basically, it's not maximum bipartite matching, but I am weak on this part. I thought vertex cover is NP, but that's why I'm also a little bit confused. No, it's linear programming, huh? Yeah, I thought this was NP. That's why. Okay. I was trying to find a formulation in which this is an NP, but I don't really know how, or like, I don't know. I'm not really practiced about it. But I would also say that half an hour in, this is one of those things that if you do know is NP, then you stop looking for a non-NP or a polynomial time solution. Maybe there's a pseudo polynomial time solution or something like this, but and maybe that's why I'm not getting it, I suppose, because even though I'm not if I could solve this, then maybe I'll win a lot of money or whatever, right? Okay, so the reason why this is a vertex cover is basically if we're removing this, then I don't know how. Let me just read the hints then. Fine. The set of well, from this I knew it was a vertex cover, but if you remember, so on the smallest set of vertex such that every edge has an endpoint in this set. Yeah, I mean that is what I got, but I thought it's NP though. I'm so confused. Isn't minimum vertex cover NP? Am I just like confused? Well, in any case, I mean, I guess maybe that's just in a regular case, but in a bipartite graph, maybe that's why. Okay, so then now this is max flow, which is ridiculous. Was this 300 square? I mean, I know how to do this, but I was. I think I was trying to figure out more. I think I was trying to figure out a simpler way of doing it from first principles. I mean, if this is, you know, if this is just knowing certain, theory, but I would also say that I didn't recognize it because it's been a while. Um, hmm. All right, I'm just reading this, so I'm not gonna lie. At this point, it seems like it's just one of those algorithms that I'm not, you know, and this is also one of those things where if you get on a contest, or well, I mean, get on a contest, I guess it is what it is. But if you get it on an interview, I mean, it is what it is. I don't know this one. It seems like, or I mean, I did know this one at some point, but this is something that I have not seen in about 20 years. I know the bipartite. I mean, I know the maximum bipartite matching type thing, but not with respect to this particular application of minimum vertex cover for bipartite graphs, which is just like a really, really specific things even for me. Okay. So how do we solve this then? How do we construct the max flow? But the way, or like the max flow that I usually have is like way complicated or very expensive. So I don't know that I can use max flow for this one, or like the way that I know of it. You can maybe use linear programming, but that's just ridiculous, right? Let's take a look at discussion. Maybe I give up a little bit. Maybe not. Oh, the hints and the prompts are wrong. Hungarian. I mean, yeah, that's the other way to do the pipeline, but wow, that is silly. From my understanding, it seems like the prompt is just wrong. I mean, apparently there's Hungarian, but I guess we're all learning something today. I may not submit this one just because on principle this is silly. Yeah, Hungarian is way different. I mean, I know Hungarian as well, but I generally don't use it, so that's why I don't. Or like, how often do you use Hungarian in a contest? I don't know. Leave me in the comment if you ever seen it before. This doesn't really, for me. This is it tests knowledge, which is maybe fine, but it doesn't really test problem solving because I think this is, given this is very straightforward. Like they say, Hungarian is n to the cube. That's why I didn't really think about it. I mean, even max flow for me, the way that I write it is about n to the cube. Maybe even d square, which is also n cube, right, for this problem. So I don't know what to say because the number of ones, there are a lot of ones. That's really why I didn't really consider those. But yeah, yeah, I was testing greedy just to see, max 4 would be the way to do, I usually do Edmund Cobb, but yeah, this is silly. Max 4 is like a really deep research problem, but I think this is wrong, right? Is that what they're gonna say? Yeah, I mean, I am gonna upload this video, but without a solution. I don't feel like, especially in Python, I don't even know if that will be fast enough. I mean, I guess I can set this up using a NumPy or something, but I don't know. I don't really feel like. I don't really feel like. Yeah. No, Edmund Cobb. So, yeah, this is usually I do an Edmund Cobb. So this is I haven't. I don't remember if I've done it in Python. I think I did max flow before in Python, but and then just see if we can flow. I mean, that makes sense. I don't know if this is going to be fast enough though. Is this not a bipartite graph? No, it should be, right? What is this test case? Oh, this test case. Oh, this is the test case I got wrong, right? Oh, yeah. I mean, I guess this is max flow. But I don't think it'll be fast enough. That's why I'm so confused. And the way that I implement it, like I said, is there are a lot of ones. I don't know. I am gonna upload this video, so yeah. I mean, hopefully, if you are solving this at home, and I might come back to it at some point, but right now I'm just too tired, and also this is silly. But and I. Because this is at best. Oh, let me just at least write for people who wants to look into this. I can go over this. I think I understand the solution, but I don't really feel like yeah. Yeah. This is basically this is but I don't feel like implementing something that's silly. I don't know. Basically on a bipartite graph, and this is apparently equal to maximal bipartite matching, which you can solve using Hungarian or max flow, which usually is n to the cube, where n is number of ones. So I don't know even how to. I mean, if I'm relying on the input to be weak, then this is why. I don't know. I'll come back to solve this at some point, or like I don't know. I mean, this is mentally solved. I'm just mentally saying that this problem is silly. And just to be clear, max flow is a topic that's generally speaking, network flows in general is generally speaking a graduate level course in a lot of CS criteria. Maybe there's some like maybe it's a senior level course if you're really advanced or something like this. But so like it is really honestly one of the silliest thing. I thought there may be a max flow. I think I mentioned it, but But yeah, you're probably not gonna get this on an interview unless, I don't know, you're doing operation research or something funky like that. And even then, probably still not, because these things are research problems all the way for the most part. Um, you know, so yeah, that's all I have for this one. I don't know if this is the first video that I have done with ourselves, but lead code quality has kind of gotten worse and worse. So I don't know. There's always a first for anything or everything. So hopefully, this at the end, this explanation at the end, kind of allows you to try to solve it. I kind of don't want to. I don't. That's all I have for today. I'm going to do the contest later. So yeah, stay good, stay healthy, take good mental health. I'll see y'all later and take care. Bye bye.